dead easy. They're just hard to remember the actual signs. After that, it's really straightforward, honest. Logic gate is just to do with switches, all right? Because it's all in binary, ones and zeros, it's about transistors and switches. So all you need to know is different way of transferring instructions around. Three types of gate we need to know. First one, AND. So both things need to be on with an AND gate, or only one thing needs to be on, and NOT is the opposite. So it's the easiest one to remember of the lot. I'll show you what I mean. But there is something called a truth table, which is every possible input and output based on the gates that you're given, which I'll show you as we go through. So this is what we call an AND gate. All right, an AND gate looks like this. Look, you can see that's the terrible drawing. That's an AND gate there, drawn by an idiot. But you get the idea. Now notice both inputs need to be on for the output to be on in an AND gate. If one of the two inputs is off, the AND will output an off. That's why our truth table, which always starts with 00 and always ends with 11, it'll be if the input are both off, well, the output will be off. If one input is on, that's not enough. They both have to be on for an AND. So both truth table bits where the input is one off, one on, well then that'll be an off or zero output. The only one where you'll see the output is on or one is if all inputs are also on. The next logic gate is an OR gate, either or. That's the way to remember this one, either or. So the shape's a bit different. Look, it's got an arch and then it's a bit more pointed. But either or gate is basically as long as any value input is on, so any value input will result in a positive output, which is why there's only both zero inputs equaling output. Otherwise, it will always be a positive or a 1 output, because as long as one input is positive with an OR gate, it's going to be positive. The last one that we need to do is this one, a NOT gate. NOT gates just do the opposite. So if it's not on, it's off. And if it's not off, it's on. And that's why there's only one input in a NOT gate. Now occasionally they mix the two. It looks really complicated, but it's dead easy. Look, this is a double AND gate, an AND. You can have AND ORs or ANDs or AND NOTs or whatever. This is what we call an AND, and then in brackets it'd be AND. So you can see there, AND gate, which means the first two inputs go into an AND, and then the second two inputs, including the result of the first logic gate, go into the second. That's why it's AND, and it feeds another AND gate. All right. Now you'll notice that the result has to be, because it's an AND gate, both have to be positive. So if just one of those becomes negative, so if that becomes 0, then that becomes 0, which means a 1 and a 0 means that becomes 0. Because AND, all of the inputs need to be 1 to output a 1. Right? Which is why, look, our truth table, you can see all of them are 0 unless all three of these are positive or 1, which case leads us here. If it was an OR, these would all be 1 except for this top one, which will be 0. So that's how it will work. It just work through them, but you can see, look, Q, which is our output, equals A and B, and then the result. And that's it. That's all it works like. It's just working through them one at a time then. Most of the time you'll have a smaller number than this, but if you get an AND gate, that's how you draw it. If you get an AND OR gate, it'd be the same, but with an OR, like that. And if you get an AND NOT gate, it'd be like that. And that's just the difference, really, instead of that one. Right? Maybe make your ORs a bit better than mine, so a bit more like that. That's a bit more like it. That's a better OR. But that's it. That's logic gates. This is how it looks in the test paper. So you got to label them. Dead easy. That one's and that one's not. Triangle. One input means not. Sort of rounded but straight line at the back. And this is completed. So label it. So that's your and that's your not. Now if A and B are 0, well then Q would be 0 here. But because 0 is not going into a NOT gate, that means it becomes a 1. So our first answer here is a 1. Again, look, A and B have to both be positive. So 0 there means that's 0, which means that's 1 because it goes to a NOT. 0 here, 1 here, whatever it is, whatever order of those two you do, it would always equal a 1. The only one that's tricky is if they're both on. So we'll run this one through. If, let me rub these out so you can see them. If they're both on, 1 and 1, that means the output for this AND gate, because 1 and 1 are both 1, that means it's 1 output. What is not a 1? Well, it's a 0. That's why this reverse would be unusual. But that's the logic. That's a really nice 4 marks if you get that, by the way. Rub your hands together.